All right, so today we're going to talk about limits involving infinity, both limits that are equal to infinity and limits as x goes to infinity, two different sides. So first of all, horizontal asymptotes. This is the way a horizontal asymptote is defined. The line y equals b is a horizontal asymptote of the graph of the function y equals f of x if either the limit as x approaches infinity of f of x is equal to b, or the limit as x approaches negative infinity of f of x is equal to b. Now, when you did rational functions last year in pre-cal, anytime you had a rational function and there was a horizontal asymptote, it was the same on both ends. You remember that? There are some functions where it's only on one end or the other. I think I have an example of that. Oh, actually, I know I have an example of that. So let's look at this one. This example is not a rational function. Now, it is a ratio of two functions, but to be a rational function, it has to be the ratio of two polynomial functions. What we have in the denominator is very much not a polynomial function, right? Because it's got a square root. There was one similar to this on an AP exam, I don't remember how many years ago, a fairly long time ago, that they ended up, it was on the multiple choice, and they asked something about asymptotes about it, and they ended up throwing the question out, which is, in all the time I've been teaching AP, I've never heard of them throwing out a question. And the reason they ended up throwing it out is because it was completely non-predictive of what kind of grade you would get. People who got fives on everything, who would have gotten a five, missed it at a high rate. People who made ones, a lot of them got it, but a lot of them missed it. It was completely non-predictive. So the problem is that most textbooks only dealt with rational functions. And students who had had a good grounding in pre-cal, they're like, yeah, I know the rational functions, I understand that. So here's the deal on this one. You've got this square root of x squared plus 1. Notice that is always positive no matter what. It will never be negative. It will never even be 0. Right? So here's what we're going to do. We're going to go, okay, let's look at the limit as x goes to, let's start with infinity, of f of x. Now, we cannot substitute infinity in, because infinity is not a number, right? But we can kind of think about it a little bit. And when you think about this, let's look at the denominator specifically, because that's kind of where all the problems occur, right? As x goes to infinity, the square root of x squared plus 1, what has almost nothing to do with what's happening in the denominator? What has the least effect? The plus 1. The plus 1 doesn't add much, right? It adds a 1. So there's not much effect there. It turns out that when you have something like that, remember when you did rational functions, didn't you frequently look at just the highest power of the numerator and the highest power of the denominator because the other ones didn't matter much as x got large without bound? Well, same thing here. So the limit as x goes to infinity of f of x is equal to the limit as x goes to infinity of 3x over the square root of x squared. That plus 1 in the denominator has so little effect as x goes to infinity, it is negligible as x goes to infinity. Now, I'm not saying these two functions are equal to one another, but I am saying their limits are equal to each other. Okay, now, anybody know a simpler way to write the square root of x squared? I slipped and said it, of course.
X.
No. I started to say it.
Oh, well.
Yes, what is that?
I don't know what.
You got to know the words.
Absolute value.
Absolute value. This is the same as the limit as x goes to infinity of 3x over the absolute value of x. Now, as x goes to infinity, the absolute value of x will just be x, right? So that's the limit as x goes to infinity of 3x over x. For really big values of x, what does this go to? 3. The numerator is 3 times the denominator. Well, now let's go the other way. The limit as x tends to negative infinity of f of x. We can still do the same thing here. We can go, okay, that'll be the limit as x goes to negative infinity of 3x over the square root of x squared, which we said is the limit as x goes to negative infinity of 3x over the absolute value of x. Now we got to think a little bit more. As x goes to negative infinity, what is a simpler way of writing for negative x values? What's a simpler way of writing the absolute value of x? I'm sorry? Okay. I thought someone said something, but... So if x is a negative value, right? How do you take its absolute value? Okay, so if I'm at negative 17, what is the absolute value? 17. Mathematically, what operation? You do what?
Multiply by -1.
You multiply by -1. Okay, so this is going to be the limit as x goes to negative infinity of 3x over the opposite of x. And there are many times, I'm old enough to remember when people used to say the opposite of x instead of negative x all the time. And it's actually a better thing because it's not negative at all, is it? It's just the opposite of what this is. So if I have 3x over the opposite of x, that's -3. So the horizontal asymptotes, there are 2 of them. Y equals +3 and y equals -3.
Why would you bother with the absolute value signs if it's just like how you multiply it? Like, okay. So I'm having trouble wrapping my head around absolute value being like how far it is from 0, and then like switching around and being like actually it's just you multiplying it by -1. Like I understand like the process, I just don't understand why those 2 things are equal to each other.
So if you have a negative number, then the absolute value is the opposite of the value that you put in.
Right.
So that's the same thing as multiplying it by -1, isn't it?
Well, yes.
So I'm not sure. I don't know that I fully comprehend the question.
Like I'm not sure if it's like a fully formatted question.
No,
So that
it's
might be
okay.
why.
I have those all the time.
Like if the absolute value is like this is how far it is from 0, why is it okay to multiply it by -1 just because it ends like in the same result?
Because they do end in the same result.
Okay.
Yeah.
That's cool. That's the answer. I was just like wondering why.
Yeah. It's one of those ones where it's like these 4 negative values of x, those 2 things are equivalent.
Okay.
Okay? Yeah, I was having trouble following that at first. If we have time later in class, and I have been bad about time management already this week, we will look at this graph. It's kind of interesting. Okay? But let's take a look. All right, so remember that with limits, if you have 0 in the numerator and something non-zero in the denominator, that's going to be 0, right? Okay, 0 over 3, that goes to 0. If you have something non-zero in the numerator and 0 in the denominator, as a limit, that's either going to go to positive infinity or negative infinity. It depends on a couple of things, and we'll look at some of this in a little while, but it depends on, is this non-zero positive or negative? And am I going towards 0 from the right, or am I going towards 0 from the left? That affects it as well. So both of those things become important. And then I think these are easier. Infinity divided by something non-zero. You know, you take infinity and you cut it in half, and infinity says that tickles, and it's still infinite, right? It's a little bit like cutting, I don't know. I was going to say a jellyfish, but that sounds cruel. But something like that, you cut it in half, and you're like, okay, well, it doesn't really make much difference, okay? And then if you have a non-zero divided by something that is going to infinity, that is 0. You take 3 and divide it by 40 bazillion, you have a really small number near 0. Okay, so let's take a look at these. So the limit as x goes to infinity of sine of x over x. The numerator doesn't go to a particular value, does it? But is it limited in its values? Yeah, sine only goes, the output for sine only goes between what and what? 1 and negative 1, right? So I have something that is smallish in the numerator over something that is infinite. What is that going to be equal to? 0. And occasionally students will go, well, won't this be oscillating in the numerator? Yes, it will be, but you're dividing it by higher and higher things. So what's going to happen is you're going to have what's called a damped oscillation, where it gets, what?
Sorry, that was just a really gross term, but I'll let you.
Would you rather I said a moist
No,
oscillation? Where it's oscillating back and forth, but it's oscillating less and less. Sort of like if you do an actual pendulum in the real world, you start it and it's going back and forth, but it gets, the swings get smaller and smaller over time. It's kind of like that. I have an answer.
So when this situation, so the psi x is infinite at the top, and the x is non-zero neighborhood.
So this doesn't fit any of those patterns exactly. But what we can say, well, if you want to prove it rigorously, you can do this. You can go, all right, I know that negative 1 is less than or equal to sine of x is less than or equal to 1, right? And therefore, negative 1 over x is less than or equal to sine of x over x is less than or equal to 1 over x. You agree with that also? Okay. So then I can find, well, what's the limit as x goes to infinity of 1 over x? Zero. Right? You're dividing by bigger and bigger numbers. And the limit as x goes to infinity of negative 1 over x.
Oh, it's still 0.
It's still 0. Therefore, do you guys know that symbol for therefore? The 3 dots?
No.
I use it all the time.
So,
Gotcha. So it'd be the limit as x goes to infinity of sine of x over x is 0 by the sandwich theorem. Most of the time in calculus for limits, we're kind of using limits for other things. So I'm not going to go, show me why this is true. I'm going to be happy that you look at this and go, oh, that's 0, and we're done and we're moving on. Okay? All right, for this one, anyone have an idea of what we might do to help us approach this problem? Pardon? You can't factor an x out of this because it's not sine times 5x. It's sine of 5x.
Oh, we can't move the 4x. No, it's not.
Move it to where, Ohio?
Make it 4x over x plus sine of 5x over x.
Indeed. So be the limit as x goes to infinity of 4x over x. I'm going to need to put parentheses around this of some kind. I don't care whether you use brackets or parentheses, doesn't really matter. Plus sine of 5x over x. What does that first term go to as x goes to infinity? 4. And what is the second term going to go to as x goes to infinity? Still goes to 0 because sine of 5x, it just oscillates faster. Right?
Oh, yes.
So this is just 4. Okay? So in a lot of these cases, we're not going to spend a lot of time in the weeds of going, well, I have to really, it's like, we're going to zoom into it. It's like, yep, that limit's 0. Okay? All right. Because mostly because this is a means to an end. All right, end behavior models. You looked at these in pre-cal. At least I would hope that you did. So if we can find the dominant term of some function as x goes to positive or negative infinity, then we can say this is the end behavior model for this. And sometimes the end behavior model for what's on the right is different than the end behavior model for what's on the left in some complicated functions. If it's a rational function, it's the same on both sides. But for anything else, for some things, it's more complicated than that. So if it's a polynomial, the dominant term as x goes to plus or minus infinity is the leading term. Now remember, the leading term doesn't mean the first term, does it? What does it mean? Yeah, the term with the highest power. All right, page 2. So let's look at a couple of rational functions and find end behavior models. So here, the limit as x goes to infinity of f of x, again, always be sure you have the limit as x goes to infinity or 1 or whatever it is of what? You have to have an object. It would be a little bit like writing the square root equals 7, and you're like, square root of what? There has to be an object that has to be operated on. Remember, for the polynomials, we just need our highest powers, our leading term. So that's going to be equal to the limit as x tends to infinity of 2x to the 5th over 3x squared. The constant multiple, you can actually factor out of that if you like. Most students don't do it, but you could write the 2/3 out here of the limit as x tends to infinity of, well, what's x to the fifth divided by x squared? X cubed. X to the cubed. And as x goes to infinity, x cubed becomes large without bound, right? Times 2/3. Again, it's like, okay, 2/3 of really enormous is pretty enormous. This is infinity. One note before we go on from this problem. Could you say that this limit does not exist? Yes, because it doesn't go to a particular value. But the reason we say that it's equal to infinity is because that tells me why the limit doesn't exist. The limit doesn't exist because this becomes infinitely large. Okay? We'll always differentiate between those, but this is saying the limit, there is no limit. Why? Because it becomes infinitely large. There are other reasons why a limit might not exist. All right, let's take a look at this one. Again, this should be some good pre-cal review. The limit as x goes to infinity of g of x. Well, that's going to be equal to the limit as x goes to infinity of our leading terms, so 2x cubed over 5x cubed. What does that go to as x goes to infinity? 2/5. The power in the numerator is equal to the power in the denominator, so all that's left are the coefficients. Here is an interesting one. Oh, and I apologize. I didn't actually write the end behavior model for this. Okay? So the end behavior model for this would be y is equal to 2/3 x cubed. And the end behavior model for this would be just y is equal to 2/5. This next one's a little bit more interesting because what happens at infinity and what happens at negative infinity are two entirely different things. So let's look first at what happens if we take the limit as x goes to infinity of h of x. As x goes to infinity, well, x gets really big. Duh. What does e to the negative x do as x gets really big? Small near what?
0.
Yeah, small near 0. Okay? So this part goes to 0. So this is going to be the same as the limit as x goes to infinity of x, which is infinity. So the right end behavior is y is equal to x. On the right, this is just going to look like the line y equals x. What about on the left? You know left and right can never agree. Thank you for the courtesy chuckle. So now we put in a large negative number for x. Does e to the negative x still go to 0 if x is a large negative number? No. In fact, It is an enormous number because e to a power goes up very, very, very quickly, right? It turns out that this is going to be the same as the limit as x goes to infinity of, negative infinity. Let me fix that rather than just write it in. You can barely see the negative on the other one. I should probably write that better. Of e to the negative x. Although the x becomes large without bound, taking a number like e and raising it to that power is even bigger. This is going to be infinity. So it turns out that both ends go up without bound, but for totally different reasons. The left end behavior model is y is equal to e to the negative x.
Question.
Answer.
How can you know that there's going to be the left and right hand here?
It's a really good question. If it's a polynomial function or a rational function, the end behaviors are the same. Those are the ones you spend a lot of time studying in pre-cal, right? Anything else you got to think about.
So only
A polynomial, so x squared minus 3x plus 5, that's a polynomial. A rational function is a polynomial on top and another polynomial on bottom.
because last year I wasn't really familiar with the name of the functions.
Gotcha. We will try and fill that stuff in, but we got to get it filled in quickly. Okay? Again, if we have time at the end, I want to make sure we get through everything, but let's look at that one also. Let's look at the graph of that. All right. So infinite limits as x approaches a. The line x equals a is a vertical asymptote of the graph of the function y equals f of x if either one of these two things is true. If the limit as x approaches a from the left of f of x is either equal to positive infinity or negative infinity, or the limit as x approaches a from the right of f of x is equal to plus or minus infinity. We say that we have a vertical asymptote for the graph. This happens a lot in rational functions, right? You did a lot of rational functions that had vertical asymptotes, and it was where the denominator was 0, but the numerator wasn't equal to 0 at the same time. Because if they were both equal to 0 at the same time, what usually happened? Do you remember? It's been a while. In a rational function, if you substituted in some value for x and the numerator was 0 and the denominator was 0, usually what happened on those with rational functions? Usually there was a hole. The mathematically correct word for that hole is a removable discontinuity.
Oh my god.
I like that better.
I like holes.
Well, and it's called a removable discontinuity because it's discontinuous,
Yep.
right? And you can remove it by being the little. You guys don't know this story. No one tells this story anymore. Do you know the story of the little Dutch boy?
Does he sell toaster strudels?
No.
Oh.
So you can plug the hole just by filling in the one gap. The story of the little Dutch boy was this is an old fable. I don't know all of it very well anymore. It's been a lot of years since I heard it. But basically there was a hole in a dike that was holding back the water. In a lot of places in that part of Europe, there were places where the land was actually kind of below sea level. And so they built these dikes to keep the water from flooding it. And so it was leaking, and he went and stuck his finger in it to save the town, basically. Because if you don't, if there's a leak in it, like imagine a leak in a dam,
Yes.
right? If that is not plugged soon, the water pressure starts wearing away everything, and eventually it breaks. So by putting his finger in the small hole,
What a sacrifice.
Oh no, I'm gonna stand here.
I'm gonna have to find this story now.
Did he ever live?
I
don't
mean,
think so.
The wall blew up and he died.
yeah, I feel like his finger's not strong enough to.
They
Water
collapsed
current?
on it.
Yeah.
Actually, because you're not, once you have your finger in there, you're no longer
Yeah.
fighting the current.
Wait, this isn't a true story, right?
Why would
No.
it be a true
Oh.
I said it was a
Dude,
fable.
Some Dutch kid just shoves his finger in the dam.
All right.
Other things have happened.
So
Uh,
if the numerator is non-zero and the denominator is 0, that almost always means you're going to have a vertical asymptote there. And you did a whole bunch of those in pre-cal. Okay, I promised, I said that we wanted to look back at these. Which ones did we want to look at?
Let's do the first.
Oh,
first one
3x
and
over the
last
square root of x squared plus 1.
Yep. The first and the last one.
Let me see, do I have Graphmatica on here yet?
Okay. You're fine.
What?
That's so good.
Well, I mean it, so.
Hey, Mr. Davis, who would win in a fight, me or Lily?
Oh, you've asked, did you already ask me this question?
Oh yeah, maybe it's
He
now.
said me anyways.
That's an interesting question.
Oh, no.
Wait, why is it interesting?
Well, because I feel like you might be feistier, but she has like greater reach.
Speak.
So I think it would depend on what you were fighting about.
Ooh.
Yeah.
What do you want to fight about?
Whether or not. Who's that dude who was like in World War II for Britain? He,
Churchill?
yeah, whether or not he existed.
He definitely exists.
Definitely existed.
I mean, I don't know what you're talking about.
And see, that wouldn't be one of the things you would fight over, because you don't fight with people about things that are stupid like that.
Oh, we've actually
Lily
already
likes
fought
to
over
pick
it.
a lot of stupid fights.
I'm just bored a lot. So.
All right, so let's take a look at this one. I thought I had Graphmatica on here, which is a really cool graphing program, but
That was the nerdiest thing that's been said in this class so far.
I feel like we
I'm
could get
sorry.
a lot of
It's
there.
going to get a
Yeah.
lot more nerdy.
It's like a snake.
It's the reverse.
I'm judging you right now. I just need to
Please, judge me.
I'm judging.
so this one, we said on the right side that the horizontal asymptote was 3, and on the left side the horizontal asymptote is -3. That's what it looks like.
We're so
Nice.
smart.
And then the other one we were going to look at was x plus e to the -x.
Yeah.
Oh,
Sorry for interrupting your sleep. E to the -x.
Ooh. I don't like
The
that
check mark.
actually.
Check mark.
Yep.
It's a check mark.
It's a curvy check.
So notice over here, this is very much almost linear, right?
Oh, yeah.
It looks like y equals x, and this one looks like an exponential.
It's Nike.
Wow, it's amazing. It's like it all works out like you told us.
Yeah, I get things right now and then.
Uh,
All right. Any questions about any of that?
I forgot why how to recognize y left side, right side.
I'm sorry?
I do you remember I just asked you that how do you know that?
If it's not a rational function or a polynomial function, you're going to have to look and think about the left and right side.
Okay.
Okay? Y'all have a terrific day.
What?
Did you get mad at me?